inverse tangent function. Most unsurprisingly, the tangent function is not one-to-one, but we can restrict its domain to where we will still get that full range, but the function does not repeat any output values. And again, there's lots of intervals where we could do this, and it's because this function is periodic, right? It repeats this cycle over and over again, so there's lots of places where we could do this, but mathematicians have agreed on the interval -pi/2 to pi/2. But we notice that we have vertical asymptotes at -pi/2 and at pi/2, so the interval is an open interval, meaning it does not include -pi/2 and pi/2. So on this restricted domain, right, we throw out everything else, we get -pi/2 to pi/2 per tangent. And the range, well, if I look at the range, like even if I'm just looking at one of these, right, it goes up, 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 increases without bound, and decreases without bound in the other direction. So my range is -infinity to infinity. So since inverse functions switch inputs and outputs, right, with that original function, they also switch domain and range. So the domain of that inverse tangent function, okay, well, the domain will be the range of the original. So domain can be everything, and then the range will be -pi/2 to pi/2. Right, we can look at the graph of tangent and inverse tan. So here is the graph of tangent. This is on its restricted domain, so that's the one that I kept, right? And then we can see that the inverse is going to go up here and then down here. Okay, just like our friends inverse sine and inverse cosine, we can write our function like tan inverse of x or arctan. Those mean the same thing, so we'll practice with both. For example, evaluate the expression or state it is undefined. Do this without the use of the calculator. So tan inverse of 1. So first, let's draw a unit circle. Again, we're only allowed to have outputs for arctan, or tan inverse, between -pi/2 and pi/2. And so we're saying, where does tan have an output value of 1, but again, restricted to those angles? We say, well, that happens at pi/4. Okay. Where do I have an output for tangent at that is -√3/3? This one is a little confusing because it's not necessarily like on the tip of my tongue. But what I would probably do is tangents are going to be negative down here in quadrant 4, tangent negative, tangent's positive in quadrant 1. Okay, and I want to know, when is my output value -√3/3? And if I wasn't sure, but I was sure that it was a unit circle, right, like this is without a calculator, I was trying to do it like that. I would probably, let's see, I'm not going to try -pi/4 because I know that that's where sine and cosine are the same, and sine over cosine is equal to tangent, so I'd just get -1 there. So I'd probably try, like starting out with, that's not the best drawing, but -pi/6. Try that angle here. And just kind of try it reverse. So I go, well, at pi/6, I would say sine of pi/6 is -1/2. Cosine, oh, and I'm sorry, I meant negative pi/6. Cosine of -pi/6 is √3/2. Sine of -pi/6 over cosine of -pi/6. Okay, well, what's this? This is just tangent. Okay, well, what do I get? I get -1/2 times the reciprocal of √3/2, which is 2/√3. But I can see that would give me -1/√3, but when I rationalize the denominator, I get √3/3, but it's, again, negative. That's what I wanted. So what I can see is that there is an angle between -pi/2 and pi/2, such that when I take the tangent of that angle, I have an output that matches what I have here. So tan inverse of -√3/3 is equal to -pi/6. we want to be able to evaluate expressions involving the composition of tangent and inverse tangent. Let's consider the best case scenario. So the best case scenario is when my input matches my output, and so if I'm given an expression like tan inverse of tan of x, I say the whole thing is just equal to x, where x is some angle. But this can only happen when x is in negative pi over 2 to pi over 2, because tan inverse, right, only has outputs in that range. And so for the input and output to match, then the input would also have to be in that interval. If that is not the case, if x does not start out in that interval, the inputs and outputs won't be equal, but I can find them with some extra work. In case 2, I have tan of inverse tan of x is equal to x. Well, tan inverse can act on anything negative infinity to infinity. So I'm good there, and it's not going to be undefined, so I just have kind of this happy case. So when I have case 2, I know I'm just going to get that easy answer every single time, and I'm not going to have to worry about it being undefined. Okay, so let's look at some examples. Evaluate the expression or state it is undefined. Do this without the use of a calculator. Okay, so what about arctan of negative pi over 3? Well, which case is that? That is case 1. I look at negative pi over 3. That is in the interval negative pi over 2 to pi over 2. So this whole thing is equal to negative pi over 3. Okay, don't need all this room just because it's in that case 1. Tan inverse of negative 1. Now I'm in case 2. And so I know that tan inverse of negative 1, I'll find some angle and then take tan of that. It's just going to give me negative 1 again. And again, it's because I'm in case 2. What about this other thing? So tan inverse, that's still case 1, if tan inverse is on the outside, of tan of 5 pi over 9. Well, where does 5 pi over 9 live? It's a little tricky to see, but we know that if x is in negative pi over 2 to pi over 2, then we kind of get this easy case. Is 5 pi over 9 in here? Well, we kind of have to look. 9 pi over 9 would be pi. So 4.5 pi over 9 would be pi over 2. But I have 5 pi over 9. So I can see that 5 pi over 9 is greater than pi over 2. So I'm not in that interval. So I'm up in here in case 1 where I have to do some extra work. Again, I'm going to draw this out. So where is 5 pi over 9 live? Well, we just said it's bigger than pi over 2, but just a little bit. So I'm going to be in quadrant 2. So here's my angle, and this is the angle, 5 pi over 9. Okay, so the tangent of 5 pi over 9 is some value. Let's just call it b. B. Okay. And then I say, where in negative pi over 2 to pi over 2 will I have that same output of tangent? Well, here's the cool thing about tangent. It repeats every pi, right? Its period is just pi units instead of being 2 pi. So in that case, we've kind of lucked out with tangent. And so I can see that tangent is going to repeat the same output value every pi. So if I take this angle, I can also draw the angle that is a half rotation, right? It's just going to be across. It almost kind of extends along the other side, okay? Like if this was a whole line here, I'm really just drawing the other side, okay? And so then this angle that I've just drawn, okay, if I draw it in, right, its standard position, okay, it is going to have that same tangent value. So I don't know what it is, but I can certainly find it, okay? Well, if they're just pi away from each other, that's when I'm repeating the same I'm repeating the same tangent values, then I can take 5 pi over 9 minus pi, which is 9 pi over 9, and get negative 4 pi over 9 to get that angle there. So this angle is negative 4 pi over 9. So let's think about what we did here. We said, let's call tangent 5 pi over 9. Let's call that value, let's say it has a value of b, okay? And then we say, okay, well, tan inverse says, where in negative pi over 2 to pi over 2, will tan have output equal to b, right? We said, well, tangent repeats the same outputs every pi. So we just need to be a half a rotation away, which is just 180 degrees away. So we do that, and we find that angle is negative 4 pi over 9.